is equal to f of x plus alpha n f alpha minus b and not ln inverse x. Then we can find some more properties here, right? Means you take f this side, f alpha x minus f of x is equal to alpha n f alpha minus b not ln inverse x. Okay, then you put some operator, means take some norm or you just operate here ln also here. Okay, so ln, okay, so what will you get this that side? Alpha n mod something, and what will you get? F alpha minus b of x, right? Then this side it is coming f alpha minus f. Okay, then this side what you do? Means you can subtract f alpha minus f plus f minus b, right? Then you bring this side. Okay, so you will get something f alpha minus f less than equal to mod alpha infinity 1 minus mod alpha some f something here, right? F minus b, right? And you are saying that for any f belongs to C of I, you are getting f alpha, right? So you can define one operator also. You can define one operator, and which is taking f to f alpha. Clear? So then obvious question is f what are the properties on f alpha? F alpha is f alpha linear? When it will be injective? What will be bound on f alpha? Right? Because f alpha is here, right? You can write this. F alpha means in next step you can write f alpha of f minus f and whole thing, right? Then f you can take out, and here you can choose b can be also having many choices. Okay, like b is equal to, you can take linear function of f. So here also you will replace b is equal to lf, then f will come out and f will come out from here, that will cancel out. So you will get is f alpha bounded? F alpha bounded. Okay, so you can discuss many properties on f alpha also. Now means we have taken f belongs to C of I. You can take if f will be in LPI, f will be in Bezow space or any higher space, then what will be the f alpha? And f is in LPI, so f is having some properties on LPI. So we have to cross check that is f alpha having the similar kind of properties. Okay, your guide has done most of the work in those directions. Okay, so means you can explore in this direction. Then we can go further and we see that with variable parameters. So you see here, before we were taking fn xy is equal to alpha n into y plus qn x, and alpha n belongs to alpha n was mod alpha n was less than 1, means alpha n belongs to minus 1 comma 1. Now what you are doing, you are replacing alpha n with some continuous function. So this fn xy will become alpha n into x plus y into y plus qn x. And what we have to see? We have to find mod alpha n infinity defined in this way, supremum mod alpha n x and less than 1 instead of constant scaling factor alpha n. Then whatever equations we were having, so we were having equation g of x was alpha n y plus qn x. This type of equation was there, right? So now if you are taking alpha n as variable scaling, then here also it will come alpha n x, okay, and x will be here ln inverse x, and this y will become g. So g of ln inverse x and q of ln inverse x. And in the same way the equation for alpha fractal function, like here f alpha x is equal to f of x, instead of alpha n what will come here, alpha n of x. So you are writing here f alpha x is equal to f of x plus alpha n x replaced by ln inverse, here right, f alpha minus b ln inverse x, x belongs to yn, okay. So now again the same thing you can do. If the variable scaling is there, then you can, like whatever Navasky madam has done, Bansali sir has done, then by taking the variable scaling you can explore things, okay. Then I just go for so you can read this paper by Wang and Yu, and it came in Journal of Approximation Theory, a nice journal. Then we see the Bansley-Arrington theorem, and Bansley-Arrington theorem means generally you know that fractal functions are nowhere differentiable, and you want to make them differentiable some places, okay. Then what you have to choose? We have to choose the scaling factors in such a way, and so fnp means pth derivative of fn, okay. So like ln x, g of ln x is there, and you want to find the first derivative. So what will you get? G dash ln x, then derivative of ln dash x, and ln x was an x plus bn, then ln dash will be an, okay. So here an will come g of ln x into an, and each time you differentiate, then an power will increase, and then finally you have to divide that side. So that's why it is coming an to power p, clear. And they must satisfy these two join up conditions, because you have to see the continuity also. Then you will get a ifs, whatever ifs was there, I cross r ln x fn x determines a fractal interpolation function g, which will be k times continuously differentiable. Further, pth derivative of g is the fractal interpolation function determined by some another iterated function system. So ln x comma fn comma p x comma y, okay. So just take your time and just think about this, and you can see means what is going on in this theorem, okay. And like when it was g of x is equal to alpha n g of, you can write g of ln x is equal to alpha n g of x plus q n x, okay. So when Bansley and Harrington was trying to prove this Bansley-Harrington theorem, then they have applied the integration approach. They have used the integration approach, and if you integrate here, okay, then this alpha n will come out, and you have to see only integration of g of x. But now when Wang and Yu use alpha n as variable scaling, so here it will be variable scaling, then you cannot do integration very easily, because alpha n was a constant, so it was coming out, but now alpha n is also a variable, and now you have to apply the integration by parts, and that will be very difficult. So I and means his guide Vishwanathan sir from IIT Delhi, we have done the Bansley-Harrington theorem, and that research paper came in Bulletin of Australian Mathematical Society, and you can see the proof. Means if alpha n is a variable scaling factor, then how to prove this Bansley-Harrington theorem. So we did not go by integration approach because it was becoming difficult. So we have taken some, like before also we have taken some script g, a complete metric space, we define an operator t, and we proved t is a contraction mapping, then it is have a unique fixed point, and that unique fixed point is fractal. So in the same way we have defined a space and have taken variable scaling, and we have proved that one fixed point, that will be fractal based on the variable scaling. Okay, otherwise it was very difficult. It was a challenge. We were discussing many days, but we did not get by integration approach. Then we thought that directly we proceed. Okay, so you can see that paper. Then I just show you my first slide, this figure, and you can see fractal functions means immediate application is in constraint interpolation. Okay, so like my guide Professor Chan is well known in this area, and Dr. Vijay is also here. He has also explored many papers in this direction, shape preservation of zipper and fractal surfaces also. Now he is using some Bezier curves also. So fractal interpolation is a modern technique of interpolation that share smoothness or non-smoothness, including nowhere differentiable of given data. A smooth fractal interpolation, fractal spline, yes, k times continuously differentiable, can generalize classical non-recursive splines. Okay, just I have said that if Qn is affine or Qn is quadratic or Qn is rational function, then you will get affine fractal interpolation function, quadratic fractal interpolation function, or rational fractal interpolation function. And if you will put alpha is equal to 0, then it is affine interpolation, no fractal part. It is quadratic interpolation, no fractal part, and it is rational fractal function, rational interpolation, no quadratic part. So with same time we are generalizing the classical interpolation theory. Okay, and traditional non-recursive shape preserving interpolation methods fail to produce a shape preserving interpolant k times continuously differentiable. Means if the data or the interpolation techniques are having irregularity, then I am writing in the second point that traditional non-recursive shape preserving interpolation methods fail. Okay, that's why we are moving to fractal interpolation function. And apart from smoothness, a good interpolant should honor geometric properties like positivity. Positivity means, I just clean this and I just write something here. So like you have taken some points here, like you have taken some 4 points something, okay, and you want to interpolate. Okay, and when you apply any interpolation technique like polynomial, rational, trigonometric, anything, and when you plot the curve and plot the curve, then it may go down, right? Okay, and you have taken your data positive, these points are positive, means first quadrant, but your figure is going in the fourth quadrant, means the interpolant you are getting, that is not positive. Okay, so means here you are taking all yi greater than 0, y means this is x1 comma y1, this is x2 comma y2, this is x3 comma y3, and this is x4 comma y4, and all y1, y2, y3, y4 are positive. Okay, so you are having the data positive, but when you interpolated it, your data, your interpolation is non-positive. So how to restrict conditions, how to find shape parameters or scaling parameters, how to constrain them so that this part will go up. Okay, and then the next is monotonicity. Monotonicity means you have taken a monotonic data, and monotonic data means, let us say it is monotonically increasing. Let us say like this one, data is your increasing, and you are plotting the curve, and the curve may be like this, maybe like this. Okay, so some places it is increasing, then decreasing, increasing, then decreasing, right? Okay, then how to constrain or how to restrict our scaling factors and shape parameters so that it will become like increasing. Okay, and then convex. So you have to take data, some convex data, something like that. Okay, and you plot the curve, Okay, so curve may be like this one. Okay, so somewhere it is convex, somewhere it is concave, somewhere is convex, concave. Okay, and you have to apply this theory and restrict your scaling parameters and shape parameters in such a way that it is always convex. It is always convex like this one. Okay, and why we are doing these things? Why we are doing these things? Okay, like you see, you want to design the aircraft. Okay, you want to design. I am not an artist, but I am trying to try. Okay, yeah, I want to try. Clear? Okay, so you want to design this. Okay, and there is any mistake from your side, then this will not land safely. Okay, and it is not like that you open your laptop, open the paint and you just draw it. Okay, you have to be very precise when you are making it. Okay, so what we have done that, suppose you want to put your interpolation figure inside this box. Okay, inside this box, then you can read our work and you see that how we are compressing these things so that it is coming in a box. Okay, and same time we have also done that, means your curve will be inside the box. Okay, suppose it is going downward this side, but you restrict your parameters so that this will be inside this box. And now another problem is that suppose you have a line, and your data is above this line, and you want to interpolate again, and the situation is that, means your curve may go like this and curve may go like this. Okay, it may cross the line and come this side, but you want to interpolate your data in such a way that it will always be above this line. So again you see our work and see how we are doing these things. Okay, then we restrict our parameters so that this will be above the line, something we are doing. Okay, same concept you generalize, for means line is like this and data is here. Okay, and same way you can do. Okay, and now mix those things. Okay, mix those things. Now suppose you want to do like this, one line is this, one line is this, one line is this. Okay, and another line is this, like this. Okay, these are two lines, and in between you have taken your some data. Between two lines you have taken your data, and now you want to interpolate it. And when you interpolate it, it does not, it may come out like this, right? Okay, and you want to preserve your interpolation between these two lines. So again you see our work and you see how we are restricting our alpha scaling parameters and shape parameters so that it will be inside these lines. Okay, and this concept you use here. Now suppose you want to make the wings of the aircraft. Okay, and this curve things you extend in surface case. Okay, like this case is there, you are putting your graph inside a rectangle or box. Now you take any surface, rectangle box will become a some cuboid or something, and you are putting some surface inside that. Like suppose you want to wrap the gifts, or you are in fashion industries and you want to wrap the clothes, and you want to put in a box, then you can use our work. Okay, so means you know the dimension of the box and surface you want to put inside, then you just set the parameters, boundary C and D, something like that, and you wrap. Okay, and same way this concept you generalize, the line will become plane. Okay, and you want to insert the surface here, right? And surface must not cross these lines, right? So you can restrict by your shape parameters and scaling factors. Means I want to say that whatever work I have discussed in curve case, you can generalize it for surface case. Okay, and then if you have work for constant scaling, then you put vertical scaling, and you can generalize the curve case as well as surface case. Okay, so there are some problems like that you can do, and like suppose you are driving a car, and if you are sitting on the driver's seat and you see the front portion. Okay, so front portion is always like this, right? Where your mudguard is there, right? Okay, person is sitting here, in front of that person is always in the, so that surface is monotonically increasing, right? So if surface is monotonically increasing, that means you apply this concept. So when they design in computer geometric design, they use CAD softwares, they use these techniques, means how to restrict our curves or surface so that it is always increasing, it should not be here and there. Okay, so I just show you yes, then smooth rational FIFs with shape parameters are well studied for shape preserving interpolation. Shape parameters help to preserve the shape inherent in data, and scaling factors provide fractality in suitable derivative. So means whatever techniques we have developed, our group or our lab has developed, so we are using these shape preserving techniques where shape parameters is there, you just fix the parameters and you have this scaling factor, and in classical case only shape parameters, no alpha. Okay, in fractal case you have alpha. So alpha ranges from -1 to 1, and again you generate infinitely many curves based on the desire of the industry or someone. Okay, then so what we try to do, we unify these two methodologies, means fractal interpolation function is in this direction and shape preservation in this direction, and we try to bridge the gap. So there are several problems like that. Someone is working on algebra, so he can see that where he can relate with fractal algebra. Okay, so someone is working on graph theory, then he can see some fractal nature of graphs or fractal theory, and someone is working like Atanu is working on harmonic analysis, so I ask him that we will bridge something on fractal plus harmonic analysis. So there are many things can be done, and means if you are working with your guide, the supervisor, then ask him to find such problems in the neighborhood of his or her research expertise and try to bridge. Okay, so I just show you the figure, and this figure is here. So I have taken 4 points, and I just show you that I found the derivative of one interpolation. Okay, I have taken rational cubic spline fractal interpolation function and I found the derivative, and you see the derivative is so irregular. Okay, and it is irregular though it is interpolating, right? And in that scheme I put alpha is equal to 0, then I put alpha is equal to 0, then it is matching with the classical, means it is the derivative of classical spline. Okay, and it is smooth. So this paper I published in Applied Mathematics and Computation with my guide, and so I close this thing here and I will go for the next presentation. So now we talk about some zipper or something. Okay. Okay, so we will start with, and I will invite sir after some time to help me in this. So we will go slowly because it contain lot of mathematics. Okay, so slowly we try to learn. Okay, so let script S is equal to S1 comma S2 dot 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 SM be a system of injective contractions. So you know the meaning of injective mappings, right? You know the meaning of contractions also. Of a complete metric space, you know complete metric space also. A non-empty compact K subset of X is called the attractor of the system S if this happens. Okay, so we taught you already these things, means it is graph of F is union of transformed copies of itself, correct? So S1K union S2K union S3K union S4K, like that. Okay, and after doing all the unions you will get the K. So means K is the attractor of the system. We also call the subset K subset of X self similar with respect to S. Okay. In our case, the maps Si belongs to S are supposed to be similarities and the set X to be R2. What is the meaning of similarities? I told you first day. D f of X comma f of Y is equal to R times D of X comma Y, and R must be between 0 and 1. And we use this notation I is equal to 1, 2, 3 up to M. In next slides we directly use I and K, something like that. So please write somewhere these notations. Okay, that K is our attractor. Okay, so after 10 slides, 12 slides, K will come. Okay, then you just think that K is attractor, and meaning of K is equal to union of this one. Okay, and I is the notation 1 to M, then is the set of indices, then I star is the means union of n vary from 1 to infinity I n, is a set of all finite I tuples or multi indices, and j is equal to j1 j2 dot 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 jn, and we write sj. So this j is j1 j2 jn, then sj will become s j1 j2 jn, and this meaning is sj1 sj2 dot 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 sjn. Okay, means composition kind of thing apply. And for the set A subset of X, we denote sja. Okay, so s1 s2 here, and you apply some a on that by aj. Okay, so we denote means when we find sj of a, that meaning aj. We also denote by g script s is sj such that j belongs to I star, the semi group generated by s. What is the meaning of semi group? Any algebraic structure with closure property and associative property, it is known as semi group. Okay, so gs is equal to sj, j belongs to I star, the semi group generated by s. Then again I infinity, yesterday sir told this, no, I infinity. So this is alpha script is equal to alpha 1 alpha 2 dot dot, it is continuously going such that alpha belongs to I is the index space. So just remember I infinity, we directly use I infinity is equal to this kind of sequence alpha 1 alpha 2 dot dot dot, and pi is a map from I infinity to k, is the index map which sends. So pi is such that I infinity is containing points like this alpha. Okay, so pi of alpha tilde will send to point this type of points, intersection of n vary from 1 to infinity, k of alpha 1 alpha 2 dot 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 alpha n. Okay, so I just hold this slide for few seconds so that you can make the notations, you can write the notations, understand them, then we will go for the next slide. Done from everyone? Okay, so we go further. Now let X be a complete metric space, a system S is equal to S1 S2 dot 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 Sm of contraction mappings of X to itself. Okay, X to itself is called a zipper with vertices z0 comma z1 dot 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 zm, and like I was discussing fractal interpolation function. Okay, there was no signature kind of thing. Okay, here they are introducing signature. So in signature epsilon is equal to epsilon 1 comma epsilon 2 dot 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 epsilon m, and each epsilon I belonging to 0 comma 1. If for any I is equal to 1 to m, and like in fractal interpolation function also we have two boundary conditions, right? ln of x naught, ln of end point, right? So here also you have two conditions, si z naught is equal to zi minus 1 plus epsilon I, and si zm is equal to zi minus epsilon I. And if you are interested in this work, then please download this paper written by Asif sir and Tetnev sir in the year 2003. Title is on self similar Jordan curves on the plane, and we try to provide you this slide today itself after the this break. And whenever you want to understand this type of construction, then just take means m value you fix 3 or 4. Okay, correct? like I have discussed fractal interpolation functions, so I was discussing all the things by taking 4 points, right? So here also you just fix Z0 to Z1, Z2, Z3, Z4 and try to think that what will be S1 Z0, what will be S2 Z0, what will be S1 ZM, what will be like that, okay? You just try to find.
We will practice in
Tutorial.
IFS style.
Okay, so we will practice. Sir is promising that we will practice these things today in the IFS style. Now you see here, same thing. Okay, so we have 5 points: Z0, Z1, Z2, Z3, Z4, and these are mappings. And sir was telling yesterday that they are having signature 0, 0, 0, 0, and in the next figure it is 0, 0, 1, 0. So like I am changing the figure, right? You just be vigilant. So I am changing the figure. Now you see. Okay. So signature is reversed and the signature is 0, 0, 1, 0. Okay. So sir will teach you all these things, that how these things are working, and just he explained the figure by taking 5 points. So you also start visualizing by taking 3 or 4 points. Okay, then it will be easy for you. Okay, then how to get this Levy curve? Okay,
Oh, no, this is
Sierpinski gasket. So sir will tell the details, means how to construct this in IFS style. Do you have program for this?
yes.
Okay. So means
But this is the picture from Sierpinski work.
yes.
In his paper there was such a picture without arrows.
Okay.
I
So sir is saying that here he put the arrow, but in Sierpinski paper there is no arrow, no directions, and
signature is.
yes. So this point he is trying to match here, and this point he is trying to match here, right? And in the same way you can construct, right? And you make the iterations more, then you will get this picture and again this picture, right? Then if you will go indefinitely, then it will become Sierpinski triangular gasket. Okay. Then there are some more theories there, means one theorem is there how to find the structure parameterization of a zipper. So again we have taken S in the same way in previous slide, with vertices like I have shown you in the previous figure. These vertices are Z0, Z1, Z2, Z3, Z4. So we can go up to Zm and signature epsilon arrow. Then take some x0 less than x1 dot less than xm. Like in fractal interpolation also you have seen, no? We have always we have taken data points like in this way, and I don't know where we put the dusters here, right? Like we are thinking in this direction, like we have we take whatever data. Okay, so we always take x1 less than x2 less than xn, right? Like this we take. Okay, and suppose data is like this one, like a spiral kind of thing. Okay, so first data is here, second is here, third is here, fourth is here, fifth is here, like that. Okay, data is like moving, like a snake is moving, like. Okay, so data is like here, means it is not single valued, these are multi-valued. Okay, clear? Our data is self-intersecting. Data is self-intersecting means it may start from here, it may go here, it may like data is like this one. Okay, so first point is here, second point is here, third point is here, then fourth point is here, then again like this. Okay, then how to interpolate those things. Okay, so this kind of work I have done in my thesis, chapter 8, means where I have taken data is not in this order. Okay, so I will send my thesis copy to everyone, means if you want then you can see those things, means how did we interpolate it for multi-valued data. Okay, so there are many things, like Bansal sir has taken only this pattern. Okay, now suppose data is scattered anywhere, it can be scattered. Okay, so one student of Chand sir is, I think, working in this direction, and he started with some taking scattered data, and he is using some radial basis function things. Okay, so you can look their papers also, in that they are recently came in the literature, so you can see that how they are dealing with this type of scattered data. Okay, so ideas are similar, but we have to fix the technique so that it can work nicely. Okay, so here can we change this? We will ask in this question that here also x naught less than x1 less than xm following some pattern, can we take irregular, can we take some scattered? No, there is no relation. Then what will happen? Be a partition of I is equal to 0 comma 1, and now script tau is t1 comma t2 dot dot tm, be a zipper with vertices x naught to xm and signature epsilon bar. So there exists a unique continuous map phi such that phi of xi is equal to zi, and this phi will commute with si. So in the next line you see si dot phi is equal to phi dot ti. Okay, so si dot phi is coming equal to phi dot ti. Okay, means the script s is having s1 s2 dot 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 sm. Okay, means one family of zipper, right? And this script t is having t1 t2 dot dot tm, another kind of zipper, right? And there must exist a unique continuous mapping phi such that si into phi is equal to phi into ti, and moreover the map phi is Holder continuous. Okay, so who will tell what is the definition of Holder continuous? A mapping phi is Holder continuous. When it will be Holder continuous? Modulus of phi of x minus phi of y less than some c times into modulus of x minus y whole power alpha, and that alpha is known as Holder exponent. Holder exponent is alpha, and c, that constant, is known as Holder constant. Okay, so that you know. I can write here, means phi of x minus phi of y is less than equal to c times modulus of x minus y whole power alpha, and this alpha is Holder exponent, and this c is Holder constant. Okay, and what will happen when alpha become 1? When alpha become 1, then it will become, in the next we are using ellipsis. Okay, so when alpha will become 1, then condition will become ellipsis continuous. So next theorem is let s is equal to s1 s2 dot 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 sm be a zipper in R to power n, and suppose all si are similarities, and let phi the same mapping be the linear parameterization of s by a zipper, that t. So the Holder exponent alpha of the map phi satisfied, means you can always find the value of alpha by calculating this last line. In this slide, alpha is equal to minimum of log of lip si divided by log of lip ti. Okay, so by that you can find that Holder exponent alpha value you can find. Now what is Jordan arc criterion? Okay, like you know Cauchy criterion, right? We studied in BSc, MSc. So here also one Jordan arc criterion. So let S, again the same thing, S1 S2 dot dot Sm be a zipper with vertices x naught x1 dot 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 xm in a complete metric space x row such that all contractions Sj such that x to x are injective, and if for any I comma j belongs to I, the set that, like in the previous first slide also we discussed about KIS intersection KJS, is empty. When it will be empty? For modulus of I minus j greater than 1, and it will be a singleton set for modulus of I minus j is equal to 1. Then every structural parameterization, that phi we are talking about in previous slide also, that phi from 0 1 to ks is a homeomorphism. What do you mean by homeomorphism? In my lecture, first lecture I told you phi must be continuous, phi must be bijective, and inverse function will also be continuous. So this phi will be a homeomorphism, and ks is a Jordan arc with endpoints x0 and xn. Okay, so we try to provide, means where we have taken these theorems, we try to provide those references. Means I just asked sir to, after lunch we can sit and provide those notes. Then lemma and disjoint periodic arcs. Now suppose that Jordan arcs gamma 1 and gamma 1 in C with the common endpoints 0 and endpoints a1 and a2 are disjoint in C minus 0, and if the similarities sjz is equal to cjz with modulus of cj is equal to qj less than 1 are such that in this way, then we were talking about here, right, this alpha, we talking about this alpha. Okay, so there will be alpha 1, so like that we will find alpha 1 and we can find alpha 2. Okay, and similarly we can find log q1 and log q2. So if both these things will be equal, alpha 1 divided by log q1 is equal to alpha 2 divided by log q2, where alpha is the increment of the argument of z along the arc gamma z dash, subset of gamma j with endpoints aj and sjaj in the direction from aj to sjaj. So here sir, I think we plotted this figure yesterday, right? So you know this, what is the name of this curve? Okay, and here means we have taken logarithmic of previous figure. This figure is there. Okay, and in the next slide we have taken logarithmic of this figure, and logarithmic of figure, and we zoomed the figure and some part of the figure we capture here. Okay, so you can see that they are periodic, in nature. Now sir told me to skip this slide. This is not relevant to our lecture, and now we are going to discuss about multi-zipper. Like yesterday I think we plotted zippers, and today in session we will see how to see the multi-zippers and dendrites. So now the definition of the multi-zipper is take skip z is equal to fe and e belongs to capital E, be such digraph system of similarities with structural graph gamma is equal to v comma e. V means vertices and E means edges, and in each space I can go a little further, and you see here diagrams are here, you can see. So these are 4 points, and here also 4 points, here also 4 points. Okay, so now these whole 4 points, okay, how to see this figure, okay, how to understand this figure, these full 4 points by this map they are mapping to this interval here. Okay, clear? Means whenever this type of arrow is there, that means these all 4 points are mapping to here. Okay, and like it is clear again, this all the 4 points are mapping to here, this is also here. Okay, and like this full here, so you can relate. Okay, so sir will demonstrate more in this direction. So what is the definition of multi-zipper? So in each space xu, u belongs to v, b means this set of vertices, we have a finite chain of points z0 u dot 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 zmu u. Okay, then there is a bijection epsilon of the set of pairs u comma I, u belongs to v and to E for any edge E is equal to epsilon u comma I, and F sends to like this way. Okay, so we will discuss this in detail after some time. And again the same thing here, means in previous slide this graph was there, and here you see that there is a line here, this kind of line, and there this is which curve? Who will tell? What is the name of this curve? Van Gogh curve? Huh? Okay, so now you see in the next slides we are trying to make the multi-zipper. Okay, so this copy is here. This copy is here up to this part. Okay, you are able to see. This is Van Gogh curve, and this side also the copy of Van Gogh curve. And this line you just see up to here, from here to here line. See, you are able to see, and the line, this line up to here. So this part is the joining up to lines. Clear? And this side and this side, they are the copies of the Van Gogh curves. Okay. In the same way, here you see the line, just the up line, you just turn it back like that, reverse, and this copy is the copy of the Van Gogh curve. Okay. Then you see here. So these are the multi-zippers. Very exciting figures, means sir showed me these figures in 2013. I think you visited IIT Madras. After Kerala conference, you came to IIT Madras first time, right? Then he showed these figures for multi-zippers. So very nice. So we will see, sir will show you these things in more details. And there are some more theorems or results, so I just read them, and so that we can become familiar with them. So let S be a regular graph directed system of similarities in RD, means d-dimensional, R means R into R onto R something, with Jordan attractor gamma arrow. If one of the components gamma u of the attractor gamma bar is different from a straight line segment, then there is a multi-zipper. Means when can you say that there is a multi-zipper? Okay. So this statement of theorem must be true, such that the set of the components of the attractor object contains each of the arcs gamma u. So there is a proposition: if a Jordan arc in plane is a component of attractor of a multi-zipper, it satisfies OSC. OSC means open set condition. What was open set condition? So some of you know exactly what is open set conditions. Okay. Okay, then we go further. So maybe from these slides, sir can explain more nicely. Sir, you want to explain from these slides? Because your part, these figures will come here, so you can relate these things more nicely. Then I invite sir, please sir come. So he was explaining this figure.
At which time we have a break?
It will be 1 hour now. You have to teach for 1 hour. Break will be at 1.
At 1. So we have 1 hour.
Yes. Yes.
And I will make a GC now. Right?
Yes.
Tutorial.
You can explain these 1 or 2 slides, then you can go for tutorial.
Yes, because I need to return back
Okay.
and prepare some. And we'll make some pictures.
Okay. It is good.
Yes, excellent. 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 Okay. So, what we have to do? So we will begin with the definition of a zipper, and we'll try to construct some. So does it work? Do you hear me? Ah, now you hear me. Okay. What is this? What happens? understand this sound?
Yeah, this is, I think my WhatsApp is open.
Your battery?
No, I just closed.
Okay, so I think we need to toggle laptops.
Okay.
Okay.
You want to use your laptop or this one you want?
Yes, it is better if I use my laptop.
Okay.
Okay.
Then it will be good. I can also work.
And because you will feel very lonely without your laptop. I cannot allow myself to make you suffer so much. So meanwhile, I am preparing my laptop. We will try to look at the definition of a zipper in practice. So maybe even having this laptop unconnected, I can explain it a little. Yes. Oh, it says no signal. Okay, yes. I have this. I have this one. Oh, no. There are many presentations, all very nice, but we need to have this one, I suppose. No, sorry. Just 1 second. This should be okay. Do you recognize what is shown on these slides? Yes. Very interesting. Why? How to make it single page. I wrote single page. Continuous plus. File. Who knows how to manage this problem? Yes. Line. And which programs? Oh, no, this is shown in TechShop. I will find it. Thank you. Okay. I just need to find this. Yes, in 1 second I will find it on my laptop, and after that I will switch, because it is absolutely impossible to distinguish super minimized letters. Curved, okay. I think, right? Yes. So this is a very old does it should connect. this is very wise. Oh, okay. So this is the definition of a zipper, and I think we need to look at it in more detail, right? So, as you remember, the first two zippers which appeared in mathematical life were von Koch and Sierpinski gasket. They were projected just in the way how we define a zipper. So it means we have a sequence of points Z0, Z1, Z2, Z3, Z4. Of course, if I try to be more economical, I can use just 3 points for von Koch curve, but I will do it in the next step. And then I draw arrows between these points. These arrows show the signature of a zipper. This is a signature. So this will mean that the signature is 0, 0, 0, 0. So zipper is a scheme which shows how we organize the similarities in a system. So it means that so we have similarities S1, S2, S3, and S4, yes? And we S1 is designed in such a way that 1, 0 goes to Z0, and 1 goes to Z1. Well, I mean, Z0 goes to Z0, and Z4 goes to Z1. So initial point and end point are mapped by similarity to two consequent points in this sequence. Yes? The same way S2 sends Z0 to Z1 and Z4 to Z2, etc., 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 etc. Yes? So this is how the zipper with signature 0, 0, 0 looks like. And if we apply this map at first iteration, we'll get the figure. The figure which I try to draw in maximally identical to what appears on your laptop. Okay, so, and suppose we change signature from 0 to 1. It means, for example, let this signature was 0, and suppose we change this signature to 1. It means that instead of Z0 being sent to Z1, it will be sent to Z2, and Z4 will be sent to Z1. Okay. So what happens with this picture? Yes. It will turn upside down. Yes? It will turn upside down. So, so how do you think? Maybe make some programming. Yes, because we need to check how it works. We can toggle signatures. We will fix these 5 points. Yes. So let us write a program for IFS style. Since these points may be quite different, we will write it in the following manner. I define that 0 is 0, that 1 is, say, 1/3, yes, that 2 is 1/2 plus 3 to the power 0.5 divided by 6, yes, by 6. Z3 will be 2/3, and that 4 will be 1. This is not the unique way. I can define these points anyhow. And now we'll define maps. So we will write S1 will be, you remember we defined the similarities, sending pairs of points. Therefore S1 will be SIM 0, 0, 1/3, 0. Right? You have some objections? Objections, questions? No? Is everything okay? Can we continue? Okay. And S2 will be S2 will be SIM so what you have 1/3 0 1/3 0 yes, not very good. This is not very good because yes, it's better if we do this way because it may be simplified, but for simplification we need to draw some additional procedures. Yes, Z2, this will be 1. Okay, so yes. So if it will be right, this way. Okay. Okay, let it be so. Yes. 3.5 to the power 0.5 divided by 6, and S3 will be SIM. So it's a very awkward construction, but it will be good for us to toggle these numbers and changing the signature. Yes, therefore let us make this unpleasant work for one moment, and after that we will make it in a different way. Okay, and then it will be 1/2 3.5 divided by 6. Yes, of course we can denote this value by some letter, and then just put this letter here. So this variable, and we have two thread 0, and finally S4 will be two thread 0 0 1 0. Okay, or S4 will be SIM of this. You see, so we have proved then, and then we write K equals S1, S1, S2, S3, S4 multiplied by K and see the result. How do you think? Can you do that? Did you do that? You will get the von Korkev, please. Please. Enjoy.
So you are taking the signature corresponding to S2 is 0.
All signatures are 0, but then we toggle them from 0 to 1, and we'll look what does the signature make with this object. This object is very good because the similarities at the endpoints are homotopes. Yes. So no matter which signature we have, these endpoints will connect faithfully without infinite self-intersections. But when we change slightly, for example, the points Z1, yes, if we change Z1 slightly, then we'll get some unpleasant consequences. Yes, and we'll do that maybe we'll do that on some 3-point examples. Yes. So first we make it very simple. What?
There is an error showing when we put V1 as 1 by 3 0, it is showing an error.
1 dimension 2. 1 divided by 3, 0. Let me look at it. At Z1 is 1/3 0. Okay. Z0 is Z1. G4, n is zipper, lower dimension is 2, Z0 is 0, Z1, Z0 is, Z0 is 0, 0, let me change it slightly, maybe it will work. Z1 is 1/3. Really, we don't need these 4 points. yes, these points are not, yes, no. Right, then you make comments, yes, sorry. So we need just these maps. This stuff is needed for reference, but not for the program. So K is S1, S2, S3, S4. Now it works, yes? Yes. This. So you will get von Korkev without any problems. It will look the way it should look. No.
Just closed. Maybe I have to run it again.
Okay.
This is some other file.
And did you...
It showed completed and it just closed.
Oh,
I'll do it again.
okay. But yes, of course, because it's better to begin in some text editor, and after that yes. So it's sufficient if you write this in a text editor. Write this and this in a text editor. Yes. But since we need to see how signature work, we need these 4 maps because we can make variations. Okay? Okay, everything is okay. Yes. So everyone, yes. So very hard work of typing. Typing is not the best part of our practice. So you had the possibility to do something on your... And okay, oh, you are... Did you make anything? Yesterday you made. We just need to, this S1, S2, S3, and S4, and then we'll toggle the numbers in S2 and change, see what changes happen when we change the signature. Oh, what? Didn't you? Yes, of course. SIM should be in your, you can copy it from some other place and put inside. Because it was defined yesterday. Yes? Okay, so then this is a zipper of signature 000, yes? To make it the signature, for example, 0100, you need to toggle these pairs. Yes, if you change the order of these coordinates, yes, then you will get a zipper of a signature 0100. Did you toggle?
Yes, sir, we are doing that.
Mm-hmm.
1 by 2 तो आएगा ना पहले point. And 1 by 3.
Really, you need not, you see, really you need not make changes. Yeah, you just write, for example, you can write S2A, yes, S2A will be SIM, and you toggle 1, 2, 3.5 divided by 6, 1/3 0. Better is Okay, so did you make this turn? Yes, you see. Now you see what the signature means for our zippers. Yes, it makes such a rotation, and if, for example, we change this signature too, then it will be a very interesting result. Yes? If you toggle these coordinates here, yes, if you make S3A will be this one, two third, 0, 1/2, 1/2, 3 multiply 3 to the 0.5 divided by 6, yes? Then you'll get one more result. Yes, if you change S3 in the reverse order, then you will get one more result. Okay. Did you get? Oh, you have.
The program for same operator.
So all these things were made in your text editor, yes? So if you jump to your text editor and then manipulate with your text, and then after that you return to IFS style. Or otherwise, there is other way if, no, of course you can make in this editor, but it's better if you work with text editor. It's more simple. So what? Yes. 1 second. Yes, you have, but you need this program. Yes. And did you make it yesterday? Yes. So just open a text editor. Yes. And in your text editor there is a program. Yes. And you can just add this block to this program, and therefore it will use previous programs after the block is added. Yes. Yes, you can. Yes, you. The source is so you have this Koch curve AIFS, yes, and you can jump. Oh no. So you. I don't remember how in Windows you can change the program. Sorry. You can jump to some text editors. Yes, and you open this file in Notepad and make additions in Notepad. So Koch curve IFS. Yes, you have this. You need to open it in the Notepad. No. Open with. Yes. No. You have a Notepad. Yes. Do you have a Notepad? Oh, yes. And file, open. And where are your IFS style files here? No. It doesn't see it. Yes, because you need to have all files. So you have just one, and when are the others? I don't know.
This is the recent one.
Yes, yes. So they are, where are they?
This is showing error.
No, no, no. You need to open it with a notepad.
Oh, okay,
Yes,
okay, okay. Open
yeah,
with notepad.
yes. Maybe this way. You see, I didn't work in Windows for many
Yeah,
years.
but still,
I have
open with.
opened with, yes,
Okay.
notepad, right? Okay. And this is a new one.
Yes.
Yes. And whereas you need also,
Oh, I just have to compile all.
yes, yes, yeah,
Okay.
you need to combine these files in Notepad. You just add this block
Okay.
in previous program.
5 by 6 is the mixed fraction. 3, 5 by 6.
3 to the power
Oh,
0.5 to the power. 3 to the power 5. Any questions? Sorry, there are, my explanation was not good. Oh,
Sir, I
no,
was
no.
able to get that. My point is actually, sir, how are you getting this? This is from the zipper sequence.
What? What you ask?
So this one,
Yes.
what it is doing?
Uh, uh, but we defined this subprogram
Yeah, earlier.
yesterday.
Yes.
Yes, it sends the interval 0, 1
Mm-hmm.
to the interval 0, 0, 1, 0.
Acha.
Yes. In our case, it's just a contraction.
Contraction.
So really, you can write that this is 1/3.
1/3 of the period.
Yes, just
And this
1/3.
one?
But and this is not 1/3. It's a translation by 1/3 0 and rotation
Acha.
by a vector similarity, which sends 1 to 1 6.
To the above.
Yes, to this difference 1 6 square root of 3 divided by 6. Yes.
Okay.
Mm-hmm.
So from that program, yeah. Okay, I get it.
Yes. Yeah. Okay. So this is okay, but what is the next? So okay, it works. And now you make. Sorry. You add. Excuse me. Instead of XP, enter. Yes. You make S3A. Yes. And you have this SIM, but you toggled first two values with second two values. Yeah. And then replace S3 by S3A. Yes. Yes, yes. Okay, so you.
Shifted the coordinates for S2. So one side you can have.
Yes, yes, I see. Yes, really, it's so. And can you do the same with this S3? S3. Okay. Oh yes, looks wonderful.
This one, sir. This one.
This one.
This is
Right,
correct.
right. Yeah.
So
Yes,
basically,
yes.
it's the signature of this and
Yeah,
this signature.
we changed two signatures, and it gives us the result.
It's okay, sir. Thank you.
Please. Okay. Right? I hear you. Sorry. Excuse me. What it is?
On that previous yesterday's
Yes. This SIM.
and that one another was it also there that
Yes. But you see. But you have only this file, or can you?
yeah
Yes. And you have test here, right? And since SIM is here, you can add something to your test. for example, or you can add block. Yes, so this is, so you can just print. So you can just print S1, S2, S3, S4 here, and try to L, change different letter for the attractor. Yes, it's okay. So, and if you toggle both, then you will have oh yes. Okay, so now you see how signature works. Okay. Did everyone see how signature works? Yes? Okay. Okay, Vijay. What?
What is the problem now? I've done everything is in the block.
Everything. Yes, and it doesn't show.
No, nothing.
Apply. Yes. SA1, SA2, SA4, KA is KA. Yes. And you said apply, but you have this.
That I don't know how it came. You can check here.
I don't understand. Where is it? And let me check here. No, it doesn't show. This is this one. Maybe I understand. So let us make some. Will it work? Fantastic. I don't know what happens, but it began to work. So, do you have some problems? Battery, yes. There is a... yes? Oh, fantastic. It looks very nice. So you see what is the signature of a zipper. It's a very important question. Okay, so if you have made a picture with a zipper and signature, let us turn to basics, because we have too many points, and as Professor Saurabh Katyar told, we must begin with 3 or 4 points instead of these 5. So let us do the following things. So you create a new block or create some new lines in your program and define the following things. So we take 3 points, 0, 0, 1, 0, and AB, right? Okay? We create such 3 points. How we will create? So you have first you need to define AB. What we'll do? We will construct 4 zippers, because we have signature 0, 0. A second will be signature 1, 0. Yes, 1, 0. Third will be will have a signature 0, 1. And fourth will have a signature 1, 1. With the same coordinates, it will be 0, this will AB, this will be 0, this will be AB, this will be 0, and this will be AB also. So we will take four such objects. They will be called maybe K1, K2, K3, K4. Yes? So what it will be? It will mean that first we need to define A and B. Suppose these points A and B are AB are the points AB runs through this square rectangle. Yes. So I write A. I define as A as some random real number. So I write that this is a number. Yes, and in the parentheses I write that it is real. And it changes from 0 to 1, or if you wish, it can change from in some smaller extent. Okay, real. Oh, sorry. I forgot what kind of parentheses are here. Round. Okay. Okay, round. Yes, because brackets are for vectors, operators, and other stuff, and matrices. So it will be 0, 1. Okay. And as far as B is concerned, we will make it a little smaller by so A, B will be also number, real, and it will change between 0, or if you wish, you can allow it to change between minus 0.5 to 0.5. Yes. Okay, so let us write this way: minus 0.5 plus 0.5. Okay, we have written these comments, so we have a freedom of maneuver. We can regulate these values in these domains, right? And now what I do, I will write K00, yes? It will be SIM of 0AB union let me write it in different way. For example, let S10 will be SIM 00AB. S11 will be SIM AB 00. S20 will be SIM AB 10. Yes, and S21 will be SIM 10AB. Okay. We defined this two variations of first map and two variations of second map. And now we write K00 is S10 union S20 multiplied by K00, right? K10 will be S11 union S20 multiplied by K10, right? The same with the K0, sorry, K01, yes. K10 will be S1 S11 union S20 S
Vacuum should be K10 because you are taking signature of
yes. 1 second. Signature 0 is S10. This is S21. Oh no. K0. Yes, S21. Yes. 1 0 1 1 2 0 is okay, and this K10 it will be S11 S20, and K11 will be S11 S21, and you multiply it by K, or it will be K01, it will be K10, it will be K11. So if you do this, then in your list of constructed objects will be these 4 objects. But the problem is that we need to compare them. So to compare them, we need to place it at some safe distance from each other. Okay. Therefore, I write some good letters. All. It will be all. It will be. So I take K00. So I will place them in a table this way. You see? I will place in 4 boxes of a table. I don't draw boxes, but just place them. So so this will be point will be 0 0. This point will be say 3 0. This point will be say 0 2. And this point maybe will be 3 2. Yes. So I write O is K00 union. Then I shift by 0 to the set K01. Yes, K01 will be here. Then I will shift by 3 0 the set K10, and then I shift by the distance 3 2 the set K11. K10 is it will 10, and this will be 11. Okay, so please do this, and you will be able to compare all these 4 zippers in one picture. They will not intersect because I made sufficiently large distance. And you will be able to change the parameters, but first you need to draw all these letters. So you have a problem with your laptop now?
I don't know.
What it is? KF. Okay, it's good. KF is. It's really so. Yes, you're right. And you suppose that you will have four von Koch curves? No. You fractals are weird. If you...
Yes, sir, we are doing.
You are doing, yes. I wish you success in your doing. What? Error. Oh, yes. It's a problem. The teaching programming techniques is a constant fight with errors. Yes. They appear from line and block. What is the... sorry. I don't see the file. Where it is? So, okay. So you opened IFS style? Right. Why it looks so strange? Where is open file? SIM IFS? Yes, I open, okay. And it doesn't, yes, it doesn't want to open. Can we open a notepad?
Yeah, it is here.
It is here, yes, okay. Let us look. SIM. Oh, you have, you just defined two subprograms, but you have no program. Let us make it first. Maybe it will be some program. It has name. You need to define a dimension.
Okay.
A dimension. Oh, thank you. I suppose you need 7, but if you choose 2, it's good. Yes. Then you save it. Right. Control S. Right. See. And then try to open it again. File. No. File. Open. Okay. Yes. Open.
Okay. Okay.
Oh, yes, I see. KA, KB, KC minus KA. That again. Continue. Return. KA, KB, KC, KA. Very interesting. Return key. Everything is defined, but KA0, KA, KB multiplied, KC, KB minus K, KC minus K, KC minus K. So everything is okay. Let me check some.
So here I have to define it as sim dot
Yes.
AIFS like that.
No, sim SIM2.
Sim2.
Change name. Point IFS. Yes.
Okay, and now we can open it.
And the same problem. The same problem. Can I? Where it is?
Just check that it is saved or not. It is here, no?
Yes.
This file is here.
But what is the extension?
It is like this one.
Extension txt.
.txt.
You need dot IIFS.
How I have to change?
You change the extension. Save as, and change the extension.
File.
Save as.
Yeah, this file I want to change.
Yes.
By,
But you need to change the extension. Yes, this Windows do not show extensions.
okay, so I have to directly write sim.aifs.
Yes, and not text documents, all documents, all files, yes, okay. Save, yes. Let me check if it exists.
Then it came. Yeah, I don't want this file. Now we can rotate sim2. Sim2. File, open. There are unsafe changes, okay. Sim2. Okay. This one, how to open now?
I see nothing. Okay.
The file does not exist.
Yes, very strange. It's a problem of Windows, but this problem is everywhere. Can you?
IFS style.
It's in this
IFS style last one.
File Explorer, right? Sim2. It is IFS. Yes, line and block, line and file, line and block 6, line and file 8. KC. So here we have maybe it's better if somebody sends you good file. Because we can enjoy this improving mistakes in. Can you share your file with him?
Yes, sir.
Huh?
I said.
Okay. Okay, so did you make these 4 objects? They are too large? No. But where is the 4 objects? I asked.
Yeah, no.
Oh, but you need all.
Yes, sir, also I applied.
Yes? Where is all? No, just all equals K00 and it, K10, and there is a very small mistake.
Oh, it
Oh, sorry. Oh, yes. Star, please, star. Okay.
now apply.
Apply, yes, look. Look at the list of all possible objects. Here. Oh, you see all? There are 4 objects, yes? And now, no, don't. Now you go here. Sorry. Controls.
Yeah, I can change that.
Okay, and did you?
I didn't get
What you didn't get? Let me look at your... so you have this one, key, yes, everything is okay. Now you can change the parameters and see how the zippers act when you change A and B, yes? So did you make them all?
There is something.
Wow.
But only 3 are there.
It's very interesting. Can we... So, SC2, SCD, SC1, SC2 multiplied by KC. Is there any kind of a mistake? No mistakes. A00. SIM works well, but why these objects are not working? So KC, KD, KC, KD, KE, KF, KC, yes, KD, KE, KF. Can I look at them separately? Oh, KC. KC n'existe pas. Yes, why it is a point? Let us
take a random A and B.
A from 0 to 1, B from minus 0.5 is, and SC1, SD1, SC1, SC2, so KC SC1 and SD1, yes? Yes, because you had 2 operators with the same fixed point. If you have a system of contraction which have the same fixed point, then the attractor will be this fixed point. It's fantastic. And now you change parameters. Here everything is okay, but where to find how to change the parameters? You see, no, not this way. There are controls, and you begin to vary them. It's changing of A, and it's changing of B. Okay, but 3 was too much. This 3, maybe 2 will be enough. Yes. Do you know how to change the parameters? Okay. I would like to show you how can you change the parameters, because it is very simple, but it must be shown. So, for example, I need to open some program with parameters. So when you press on this button, editor, yes? Look here, please. Do you see my screen? Yes? So you press the editor, yes, and editor has several options. Here you see the source, yes, but if you press this arrow, you will have some other things, controls, yes, When you press controls, then you will see the controls for A and B. Unfortunately, I was lazy. I didn't print this program, so I cannot control A and B because they are not defined in my program, but in here. And then you will see A and B here, and you can slide them by your finger. Or, okay, you understand it? Control? No. But where you have A and B? Oh, you have an A, but I don't see them. You have only von Koch-Curve. Yes, okay. A and B. Yeah, it's alive. It's alive, yes. Okay, so did you know how to control change A and B? Everyone understood. So you can make some leaf pictures in fractals, and just changing parameters you can see how to make very good one among them. But what must be shown, let me find some IFS style program with zippers. Open files. Escape. Open recents. Levy curve. Sets. Maybe this. What it is? No. I have no such program at hand. I'm at. Okay. Oh yes, I have this one. I have this one. For example, I have a zipper on 4 points, you see, and here I have 2 parameters. Is it visible? Is it okay? Yes, I have 2 parameters, and I can change these parameters. So in this picture I have shown the arrows showing the signature, yes, and the result. Yes, so this is a zipper with the signature 101, right? And I can change the parameters. This zipper is very good because it has alternate signature. Yes, therefore at each point the endpoints of the same time meet. Therefore there are no intersections. But if we change the signature, then we'll get much worse result. Let me check if it yes, this is also alternate signature, and what is about this one? And this is, yes, I have 1010, and this is also 101. Yes. If I change the signature, then it will be 1 second. source. Yes. So what happens if you have some kind of an endpoint in a zipper curve? Yes, yes, yes. Let us have a lunch. Yes. Then we can start. So the lunch break is. I have not taken my schedule. Today is